and this is a bit flipped because normally what you do is you do a lot of research and then you write a book, but I wrote books and then I did research. And so I got a couple of papers in the COVID paper pandemic that's coming out, and I know a number of people on this call have got the COVID paper bug. This is going to be presenting the most recent of those that I have done. And this paper, I gave it a very medical-like title. I even put in SARS-CoV-2 into the title to make it seem like I'm something. Anyway, but it's actually a decision theory paper, and it's pretty standard. And the main interest to this group is not going to be any fancy work I do with the theory. It's going to be showing how, if only they had economists, and in particular microeconomists, dealing with stuff, we'd probably be all saved by now. So let me give you the context for this first. So the context, and this comes from my book, is the pandemics are manageable. Whatever we thought in March, oh, it's a disaster, we're doomed, blah, blah, blah. That's not the case. You can manage pandemics. All you got to do is you got to find out if there's someone who's infected with something that's contagious. You take that person and you isolate them. And so long as you do that for most people who are infected, you don't have a pandemic. Okay. Once they're cured, you release them. So pandemics are very manageable things. But what you have to do is you have to solve an information problem. You have to identify these infected people quickly enough and isolate them so they don't infect other people. Very simple as that. Believe it or not, and I've talked to thousands now, because I've been working on this. This apparently was a novel insight for the world, but it's exactly how any of us would think about the problem. I don't claim it's a thing, but people find conceiving pandemics and every problem they're facing as an information problem to be completely eye-opening. So anyway, that's that part. So if you don't manage these infected people, what happens is they infect other people, and so on and so forth, and that sucks. So you don't, and that's kind of what we were facing. So if you don't actually solve the information problem, what you're forced to do is you're forced to send up a whole lot of things, let's call them dwellings, and you just throw everybody as if they're contagious into these dwellings, and hopefully that deals with the problem. The problem with that is, of course, they can't do anything else. Sometimes you end up doing this, which is not so good, or you end up doing that, which is also not so good if you have sort of people handling, for instance, meat. So that's not a great, but that's basically what is going on. Everybody sitting there in Melbourne from their homes knows this issue quite well. I've known this issue. I have not eaten a meal outside of this room or this house for 6 months because I'm probably scared to go anywhere. So what you want to do is you want to have a signal. If people who are infected had their nose light up red, well, then we'd be fine. We'd be able to take those people and we'd isolate them. So that's where testing comes in. What you do is, in order to identify the infectious people, you test for infectiousness and then you isolate them. So that's what you have to do. So pandemics are manageable if you can solve the pandemic information problem. So I've been focused for some months on trying to convince governments to do just that. There's slow progress being made, but there's a lot of barriers. And I'm going to talk about a regulatory one here. So what do you do currently to test people for the coronavirus or for something related to it? Well, there are basically sort of three broad buckets of things. There's something called the standard PCR test that I'll go into in a minute, which is done by this big hulking machine here. So that has to all be done in a lab. There's a whole lot of expensive. The machines are expensive. The chemicals, the reagents are expensive, etc. To run these things. So these things tend to cost about $50 to $150 per test. If you're in the US, you can pay a lot more because that's how they do things. In Australia, Canada, it's costing the government $50 to $60. There are these rapid tests, the smaller devices that you can put in places and don't have to be in labs, that end up costing about $30 a test to run by this sort of mid-time device. This is what they have in the White House testing people. They've got it at a few other places as well, but it tends not to be. They haven't been. There's some distributed, but they're not that widespread. The majority of testing in Australia, for instance, is these high-end PCR tests. That's the same here in Canada. They conduct 50,000 of these things a day, and you can imagine. So that's $90 million a month being spent on just a fraction of the population being tested. So the hope is that you have what this third test is a rapid paper strip test. You take some either a nose swab or some saliva, spit on a strip, wait a few minutes, and then it tells you whether you're pregnant or not. No, it tells you whether you've got the thing or not. These are antigen tests, and they're a little bit different. They pick up sort of chemical markers of the coronavirus, but they can do that, and they can return a result very quickly. They don't require a machine, just like a pregnancy test. You don't even need a medical professional to actually run this thing. They can be distributed the size of a credit card, between $1 and $5 a test. Currently not being used anywhere, although it's starting to be used in India more. So obviously cost is a huge issue. If I want to be testing for potentially asymptomatic people walking around being infectious, I'm going to worry about the cost of these tests, but currently we've got it all stacked in sort of the most costly option. So you'd like to move it to least costly option. Now, obviously you've got to say, well, if something is lower cost, you're getting less for it. One thing you're not getting less for it is speed. These standard PCR tests, you get the results in 1 to 2 days. Now there's a problem with that. If you're an infectious person, that means you're wandering around for another day or two before we get to find out that you're positive for the coronavirus and isolate you. Of course, we could flip that and just isolate everybody until you've got the result, but that's not how these things tend to be used. So in other words, the results come in 1 to 2 days. The rapid test in the middle there gives you a result in about 15 minutes. So that's easy. So people can wait around for that. So if you're getting into the White House, that's nice and acceptable for you. These rapid paper strip tests, the results can come in a minute. Okay, so in other words, these can be done quite readily. If you imagine if you're boarding an airline, we have enough things that cause us to wait. Waiting another minute for a test result is not going to be much of an issue. So that's not the dimension. So what's the difference between all these things? The difference is in quality of the test. And that is potential errors in identifying whether someone has the virus or does not have the virus. So false positives and false negatives are going to differ. I'm going to just have to check here whether I can do this. I'm going to optimize screen share for a video clip. Since it's late here, I'm going to play a video clip from Yes Prime Minister that will give this some context in a second. All right, so let me tell you about this PCR test. This is the process that allows scientists to identify specific pieces of DNA and actually RNA by converting it into DNA in very small samples. And it's what allowed you to do the Human Genome Project and all sorts of things. It's a huge advance in our ability to understand genetic things going on inside us. So one of those things is, of course, the novel coronavirus. And so what happens is you take a nasal swab, and you know, if you really want to make sure you get it wherever it is, I mean, problem is, you know, people blow their noses and swish around their mouth, so you've got to stick something straight up their nose, close to the, seemingly close to the brain, collect a swab. But what's the miracle of this is that you use these sort of cycles of analyzing, looking for this particular strand of DNA. And if you can't find it in one cycle, you go through a replication process, and a real replication, so you know, order of magnitude every cycle, which just replicates all of the DNA material in the sample until eventually you've got enough of the one you're looking for to actually find it. So it's as if you took a needle in a haystack. You've got a few needles there. There's one in particular you want. You can take all the needles out of the haystack and just keep replicating them until you see enough of the one you want. So these tests have these run cycles, and I mean, you might find it immediately, but there's sort of an optimal stopping point. At some point, you have to give up, and so give up after about 40 cycles. But just before that, that's like 10. You know, that's like, there was just nothing there if you can't find it in 40 cycles. Like, there's no virus. Very little could be there. So there's almost no chance of missing it. But these things, that's why it takes a day sometimes to do these particular cycles. But each cycle, the sooner you find something, it's an order of magnitude more present, the virus in you. You know, basically 10,000 times more present than the next cycle, and so on. So that's how that goes. And this is called the gold standard test. And I'm just going to play you my favorite clip from Yes, Prime Minister on this subject. It has to do with nuclear weapons purchases. You'll get the drift. Polaris was the original one. Sir Humphrey here is trying to persuade the Prime Minister to get Trident, which you'll see.
Cruise instead.
No, we shall buy no more nuclear weapons.
But, Prime Minister, you're not a secret unilateralist.
No, we still have Polaris.
Polaris is a ramshackle old system. The Soviets might easily develop a multi-layered ballistic missile defense system which could intercept Polaris.
By when?
Well, in strategic terms, any day now.
By what year, precisely?
2020. But that's sooner than you think.
And are you saying that this nuclear defense system would stop all 192 Polaris missiles?
Well, not all, no, virtually all, 97%.
Well, that would still leave, what, about 5 bombs that would get through?
Precisely, a mere 5.
Well, enough to obliterate Moscow, Leningrad, and Minsk.
Yes, but that's about all.
I should have thought it was enough to make the Russians stop and think.
But it's not fair. With Trident, we could obliterate the whole of Eastern Europe.
They want to obliterate the whole of Eastern Europe.
But it's a deterrent.
It's a bluff. I probably wouldn't use it.
Yes, but they don't know that you probably wouldn't.
They probably do.
Yes, they probably know that you probably wouldn't, but they can't certainly know.
They probably certainly know that I probably wouldn't.
Yes, but even though they probably certainly know that you probably wouldn't, they don't certainly know that although you probably wouldn't, there's no probability that you certainly would.
What?
Boils down to one simple issue. You are the Prime Minister of Great Britain. Don't you believe that Great Britain should have the best?
Yes, of course.
Very well. If you walked into a nuclear missile showroom, you would buy Trident. It's lovely, it's elegant, it's beautiful. It is quite simply the best, and Britain should have the best. In the world of the nuclear missile, it is the Savile Row suit, the Rolls-Royce Corniche, the Chateau Lafitte, 1945. It is the nuclear missile Harrods would sell you. What more can I say?
Only that it costs £15 billion and we don't need it.
Well, you can say that about anything at Harrods.
So, the PCR test is the coronavirus test Harrods would sell. And that's basically, if you read what the medical people are saying as to why you should have that test and not go for these cheap tests, it's because nothing beats the gold standard PCR for accuracy. Well, I'm going to turn all that on its head. People have been arguing, well, maybe it just, who cares? We should sacrifice, let's do the economist thing. We'll sacrifice some accuracy because we'll get it cheap and we'll get it fast, and we might actually be able to deal with this more quickly. And people from Paul Romer onwards have been making that point. But what I want to make a point is that, in fact, these cheap tests are not only cheaper and faster, but they are actually more accurate as well. And they're more accurate in an information theoretic sense. In other words, these tests dominate the currently practiced tests around the world for dealing with this coronavirus. Dominate. So let me show you why that's the case. Let's take it back, and I just need to introduce you some terms. Every discipline has their terms. We have type 1 and type 2 errors. People have false positives and false negatives. But our drug approvals, our testing things in medical science have this thing called sensitivity and specificity. And so this came from a paper in 1947, thinking about X-rays and whether you identified whatever you're looking for. And the measure of sensitivity was the probability of a correct diagnosis of cases that were positive. So given that somebody had the thing, what is the probability that your test marked them as such? In other words, it's a measure of sensitivity. It's a inverse measure of the number of false negatives you get. Specificity is the probability of a correct diagnosis for negative cases. If you don't have the thing, what's the chance that your test actually tells you that you're negative? In other words, that's an inverse measure of false positives, okay? So at the moment, these PCR tests are have very high specificity. Very rare do they get false positives because they only set up a blinking light if they actually find the damn virus. So it's very hard to have a false positive. But they actually turn out to be very sensitive as well. They can find the smallest remnants of this virus, the RNA fragments. They can find that. So that's why the medical profession is like that. The error rate on finding whether someone is infected with this virus, very low. So if you sort of lay all this out in a table, I've told you about a few things, but throw into the specificity and sensitivity, the PCR test has very high specificity, gets it right almost 100% of the time. It's only like a lab error that gets it wrong, okay? Sensitivity, they occasionally, might be some RNA there, but you didn't do the nasal swab well enough or something like that, so occasionally misses some stuff. The mid-sized test, which is also a PCR test, but is done really, really quickly, also has high specificity, not surprising. It can't give you a positive unless it finds something, but it has lower sensitivity. Only, there's 9% of the cases that it's missing. So there's false negatives. And the fast tests, and the only ones we know of sort of now, there's a few of these ones, have also high specificity, because they only blink up if they find the thing they're looking for. But they've got high sensitivity, they've got lower sensitivity because there has to be a lot of the virus present for it to pick it up. Okay, so the regulators have allowed 1 and 2 there in the list, but they have not allowed the fast, cheap test that we need to really solve this crisis. But let's have a look at this in a different set. This is the days since exposure and the viral load you have of SARS-CoV-2 over it. It turns out that you haven't seen this. I don't know if there's a mechanism for questions if anyone has clarification. So, but you can.
We just unmute ourselves and ask.
Oh, okay, good, perfect. That's fine. Anyway, so 0 is the day you got infected, the virus came into you. It takes a little time for it to sort of start replicating in your body, but you can see by about day 3, it started to really take off inside you. And then at about day 5, it reaches the peak of how much there is inside you. which could be different for different people, of course. And then it starts to steadily drop off thereafter. And that's in terms of the viral load. Your PCR test can detect viral loads as small as 10 to the power of 3. That's, you know, 10,000 bits per milliliter, which is not a huge amount. It takes about 30 cycles of it to get that. The rapid tests can detect 10 to the power of 5. So an order of magnitude more virus has to be there before those rapid tests pick it up. Okay, that's the purple line there. So if you tested someone at day 3 of their infection, the PCR test is going to register them as infected, but this other test will not. If you test them at day 5, 4 or 5, at point B, both tests will test them as positive. But here's the difference. The test, the rapid test done on day 5 will get that right away. Whereas the PCR test, especially in the US where it takes a little time, you test someone at day 3, it does pick it up, but they don't report it until you've passed the peak of the viral load. And so you've been wandering around spewing the virus everywhere, viral shedding they call it, for ages. The other thing, and this is really important, the PCR test will test you as positive on day 15 or day 18. Now, I'm going to blow you away with a fact about, as you go down that viral curve going negative, the RNA that was the coronavirus, they just die inside you. And they sort of slowly get then expelled from the body. By that time, if you've caught the disease from it, you're dealing with that, but you're not got the coronavirus as much anymore. So that viral load is going down. In other words, at point D there, if you test positive, that's testing positive for dead virus in you. Dead. So you are no longer infectious. You are no longer infectious at that point. You aren't even infecting yourself, really, because the virus that's in you is dead. But the PCR test cannot distinguish live versus dead. It just finds the RNA. And RNA tells its tales regardless of whether it's living or not, if you've watched Jurassic Park. So that's, you know, that's basically what's going on here. So you can already see the basis of the argument of this paper. Here's the thing, the other fact that I need to tell you is that you are only infectious from day 5 to day 9 or 10. 5 to 6 days, okay, of infectiousness, that you can pass this on to others. Notice that what's happening those days, you've got more of the virus. You've got so much of the virus in you, it falls out of you and into the air, and you breathe it out, you sneeze it out, you do whatever, and that's how it spreads to other people. In other words, during the time when you are so there's two things. There's a difference between being infected with the virus, which happens between 0 and 21 days, you're infected with the virus, and being infectious. You are infectious only for a fraction of that time. That is correlated very strongly with your viral load. So what that means intuitively, and I'm going to show you this in a little model, but you'll get the rest of this from this part here, is that if you use the rapid test and it only detects high viral load, that means it's a much more accurate test of infectiousness than the PCR test, which is not only detecting when you've got a high viral load, but when you've got all this other stuff as well. And so the regulators are only verifying tests for infected, treating it infected and infectiousness as the same, but they're not the same. And the only thing we actually care about for the purposes of isolation is infectiousness. So we want the most accurate test to do that. And so this is aside from cost advantages or the fact that you can do this test over and over again. Those only are, wait, there's more. These rapid tests may well be more accurate for the thing we care about. Here's the model. It's very simple. Imagine you've got theta on a scale of 0 to 1. This is a signal of your viral load. And it's distributed according to probability distribution function F. It has a mass point at 0. In other words, most people don't have any of this in them. So, and we have to take that into account. So there's a mass point at 0. A really large one. D is the decision to treat, or to not treat or treat. Don't treat as 0, treat as 1. A is the decision to isolate or not. A being the level of activity I allow you to do. So if I give you 1, you're allowed to do whatever you want. If 0, you're isolated. And then the decision maker's objective function is as done here. Over all the individuals in the population, the first term there is they get utility from not being isolated, U times AI, subtracted the cost from either being, the cost of either being treated when you don't have the virus or not treated when you do have the virus. So C there is the cost of an error. And you subtract from that big C, which is the cost associated with allowing people to be active when they're infected, when theta I is greater than theta bar, where I there is an indicator, all the I's here are indicator functions. So in other words, there's two thresholds here. There's a threshold for treatment, which is if there's a little bit of the virus in you, there might be some benefits of treatment. And then there's a threshold for infectiousness, which is a higher viral load, theta upper bar. Theta lower bar, treatment threshold, theta upper bar, infectiousness feedback, exactly as I said in the viral load diagram here. Okay, I'm going to, just a perfect information case, assume that the utility of keeping someone active is less than the cost of letting an infectious person out isolated. In other words, if we could, there's externalities and they're big. Then if theta I, you get perfect information. If theta I for the individual is greater than theta lower bar, you treat them. If theta I is greater than theta upper bar, you isolate them. Simple decision. So it's your normal decision theoretic match the decision to the state. There happen to be two decisions and two partitions, but that's okay. If you have no information, then of course you have to make a guess, and it depends on the probability masses of prevalence. If you don't know if someone is sick or not, you treat them if the probability that they're sick is higher than the probability that they're not sick when they're infected. And you isolate people if the cost of isolation is you isolate people if I think actually it's supposed to be, no, you isolate people if, come on, little things. Oops, that's meant to be a negative sign there. You isolate them if the probability that they're infectious, 1 minus F theta bar, is sufficiently high enough. And then you isolate them. Sorry about the inequality there. So what we're interested in, so that's your standard stuff. You get a test, and a test has a certain amount of the virus that it is going to detect in an individual. So suppose you had a PCR test, which means it will, for sure get you if you're infected and might miss a few of the infection bits because no test is perfect. Its specificity is 1. The reason it's 1 is that the probability that you test negative when you are negative is 1. If you don't have any virus in you, it's not going to invent some for you. The sensitivity is this calculation here, the probability that you're positive given that you test positive for infection. is 1 minus F theta, which is the threshold, divided by 1 minus theta lower bar, which is the prevalence of the infection in the population. So you'll basically treat, and we use the usual Bayesian thing here, but you'll treat it in this situation if the probability that that someone in the population is infected is greater than a half the probability that at that threshold somebody is infected. And the reason the half comes in is because I've treated the cost of the error for treatment as the symmetric either way, which of course it probably isn't, but this is not our main thing. But we can then do this and say, well, what's the value of a test relative to no test? And of course, there are two options for no testing. Either you treat everybody or you don't treat anybody. But either way, the value of information is rising in the sensitivity of the test that you have, SE theta. And it's also rising in the 1 minus theta bar, which is the probability that someone is not infected, that someone is infected in the population, which is a thing that often comes with these Bayesian things. One of the reasons we struggle at the moment with testing is even with small errors, we haven't got that many people infected in the population, so there's an error there. They're not as accurate because you will make mistakes. So that's the test for infection. What about for infectiousness? Now remember, infectiousness is are you above theta upper bar or not? Okay, so one situation could be that your test is not that great. Theta, the threshold for detecting infectiousness, doesn't get all the infectious people. So theta is above theta upper bar. Your specificity is still 1 because you can't find an infectious people unless they're actually infectious. Your sensitivity for infectiousness is now this number, which is similar to the previous one for infected, but now with F theta bar upper bar in the denominator. And so you'll isolate someone if the economic cost of isolating them, net economic cost, is sufficiently low relative to the probability that the test is accurate. And obviously, if theta approaches theta bar and becomes a sort of right at the threshold there, in other words, a positive test really says you're infectious and a negative test really says you're not infectious, then the test becomes just a perfect signal. So in this situation too, you calculate, and it's still overall prevalence in the population is going to affect the value of the test. But the important thing to know is that the sensitivity that causes you to value the test more is not a sensitivity based on infection, but tailored to infectiousness. Now, the reason why that's important is how do they calculate, when they get one of these rapid tests, how do they calculate how accurate it is? Well, what they do is they test you with this rapid test, and at the same time, they test you with a PCR test. This is what they did in the NBA bubble. And so then they see how often you match up, right? Well, that's not a measure of sensitivity for infectiousness, because the PCR test will sometimes detect very low amounts of the viral load, even dead ones, which you're not interested in. So you actually have to have a sensitivity number that's tailored to infectiousness, not off the wrong standard. So making it to the golds, if you benchmark everything to a gold standard that is not the thing you want to test, you're going to be off. And that's exactly what all regulators are currently doing. In the paper, there's more details of how that's occurring. Now, I should add that a PCR test does give you the information you need to do the right thing. So the way a PCR test or any test is reported is either as positive or negative. Are you above a threshold or not? Well, what was that threshold? Well, they chose the threshold to be, you know, fairly low, this running through 40 cycles. But they know for any given patient which cycle you found the stuff at, so they can measure the actual viral load. Well, it turns out they throw that information away. They don't report that to the doctor. They don't report that to the patient. You don't know how much viral load is in you at all, which is kind of crazy in the situation. Anyway, so that occurs. All right, but let me do the thing that's sort of more interesting is this case here, where theta is less than theta upper bar. In other words, you do have sort of this PCR test, which is far able to detect beyond the threshold for infectiousness. In that case, what's going to happen? Let me go to sensitivity first. In the case of sensitivity, if someone tests positive for infectiousness, if someone is infectious, they will test positive for infectious, probability 1. But here's the thing that won't happen. If they're non-infectious, it's not guaranteed that they'll test negative, because they might test negative for being infected rather than infectious. So the specificity of these tests are off. Now, people don't know that because they're not looking at the right benchmark, but they are. They're off. Okay? So what that means is you have to use these tests a little bit different in terms of your isolation decision. But what's critical about this, and I'll show you, is that the value of this test is rising in the specificity. But it won't surprise you that the values for these tests, depending on two cases, but I'm not going to spend too much time on that, peak at theta upper bar. In other words, if you are a PC, I wonder if there's a way I can, I know this is always supposed to be, maybe I can do this. It's always dangerous to do. Okay, so here is theta upper bar. So you're infectious if you're above it, and you're not infectious if you're not. So this is positive, negative in terms of actuality, being infectious. So if you have a rapid test that can pick up high viral load, say at this level here, okay, the value of information you get will be this. If you have a PCR test that can pick up positive or negative a viral load right all the way down here, this will be the value of the test as a decision for infectiousness. In other words, the gold standard sucks. If there's any macroeconomists here, you already know that. But the gold standard sucks. And the reason is very simple, is that as soon as you have a test that can pick up very small amounts of the virus, you're polluting your results with all these signals of positive when you're not actually infectious. And if you have one of these so-called crappier tests that only work if you've got a big viral load, you're much more likely to get people at the right hit. So as I said, I told you this wasn't going to be rocket science. From an economist's point of view, you match the decision, you match the test to the decision. And the entire world at the moment is not.
Joshua?
Yeah.
So maybe I think this is obvious and maybe you already say it, but can we do better still? Right now, I think it's like picking between different tests for one type of decision, like isolate or not, some binary thing.
Yes.
If you had, I don't know, 3 types of decisions, you know, put in a bunker, isolate with your family, you know, be able to go to a small workplace, or, you know, some gradated decisions.
Yes.
Could you do better still ignoring cost with the gold standard that came back with like 3 different buckets or something?
Right. So there's two issues. One is, of course, cost. Let's ignore that for the moment. 2, the gold standards could do so if you reported the information we need about viral load, the CT score.
Yeah, yeah.
If we reported that information, we could do much better with that. So the part of the issue is, so there's two issues. One is the cost, and the other is they're throwing the information we need away. Because they have now, to be sure, one of the problems the medical science has is they've got a good confidence of when you're infected. Find enough of a virus and they have cast you as infected. The threshold between when you're infectious or not, bit blurrier. It's a bit blurrier. You know, so they don't quite know what that number is, but they have a good idea that it's way off the current threshold. And there's plenty of people sort of talking about that. In other words, so the CT score, if you've got a CT score of 30, that means you're hardly any of the virus in you. But that's currently the threshold that people are using. Whereas if you have a CT score of 15, you're blasting the virus all over the place. And so they've done these calibrations, and our rapid tests are getting you to CT scores equivalents of about 20. So they're way into the thing there. And the problem is, but no, it's people understand cost. They understand being able to do things rapidly, but they don't understand this information theoretic thing.
Can I ask one more sort of factual question? Because you know everything and I know nothing about how these tests actually work, which is if we do batch testing with the PCR tests.
Yes.
So we put 20 people in together.
Yes.
What is it? How does that work in terms of what it comes back with this CT score?
So it will come back with a CT score, but doesn't tell you a huge amount because the CT score could be low, meaning there's a lot of virus, if there's a lot of people infected or if there's one really infected person. It's
giving you effectively some kind of average, right?
It's giving you an average. Now, so what you have to do when you do the group testing, if you come up, if the tech, look, this PCR test is so good, you do group testing at the level of a population through wastewater. That's how good it is. So it's very good at picking up small amounts of this virus. So I'm not saying you don't necessarily want to do that at all. The problem we're facing at the moment is that the regulators won't consider the cheap tests because they say they're not useful. But from this perspective, it's not clear at all. Well, from my perspective, I think they might be more useful. In other words, I would really like to know if someone on a plane has a really high viral load. I couldn't care less if they got dead virus in them.
Yeah.
Right. So that and given that to deal with this, we've got to ramp up testing by several orders of magnitude. Being hung up on this issue, you know, shouldn't even be an issue anyway. But I actually think it might actually work out even better. Is I guess what I'm saying.
Just can I also ask a question about, you know, how can we also put this into the perspective of when a test is being ordered? Because
yes, I'm going to show you that right now.
Okay, thanks. Sorry, I'm getting ahead of you.
That's all right. That's that's how this world does, doesn't it? Clear my drawings. Okay, so there's another issue. There is the issue you've just alluded to. So if you look here, I've just replicated the virus diagram that people normally have. The pink part is where, so when do I want to isolate someone? Okay, I want to isolate someone when the viral load is high, which I show here, which is between T2 and T3. However, I'm not testing all the time. So if I find someone with the virus and they happen to be a T1, right, which is very low viral load, but they're on the up, okay, I'd like to isolate that person too. I don't want to isolate anyone after T3 and beyond. So here's the issue, is that obviously my antigen fast test can capture things between T2 and T3. That's great. It'll miss between T1 and T2, but a PCR test would pick that up. So we have this interesting dilemma. A PCR test will pick between T1 and T2, which is a great time to isolate someone before they start spewing it to anyone. But the problem is that it can't distinguish between T1 and T2 positive test and T3 and T4 or positive to, or any of it at all. So that's an issue. And also, even if you did this testing between T1 and T2, it takes a while for the results to come back. So you haven't really got much of an advantage anyway over the rapid test. But really what you should be doing, if you said we can't use anything other than PCR tests, what you'd want to do is you want to take a PCR test, and if it turns out to be positive, you want to wait a few days and take it again. You'd isolate someone and then you take it again. If it turned out they're on the back end of the infection, the infection's going down, you can release them. the sad thing for most people is that they tend to test people and they become up positive, and they have to wait until you've got 2 negative tests before they release you, which means you're well past T4 before you're allowed to leave. So it's kind of like a problem. And in places where, you don't get any support for when you're isolated, you might be reluctant to have a test under those conditions. So the answer to this issue is, of course, you'd like to have that value of information would be not optimized at theta bar, upper bar, but sometime below would get you a better thing. But what you really want to do to solve this problem is to test frequently. If you're testing frequently, you'll catch those people when they're infectious if you test frequently enough. I actually think in order to get the reproduction number well below 1 and sort of stamp out the virus, a weekly test will probably do the trick. That's another, I've got a newsletter for anyone interested in this, and I wrote a thing about that a few days ago. So in answer to your question, yes, there are some issues, and this is the issue, is that you'd like to get ahead of this, but the PCR test in theory can give you that information, but it doesn't really tell you, if you're very risk averse as a decision maker, you just isolate people, but it's not telling you a huge amount. That's the problem. Okay, so the conclusions for everybody looking to find out what's going on with jobs. Conclusions is, so antigen tests are likely superior to PCR tests for the purpose of informing isolation decisions. This is great news. This should be great news to all of us because they're also cheap and they can be done rapidly. And you can imagine a situation where you have a lockdown such as you do in Melbourne, and then you say, okay, you can go to school, and you test everybody going to school. And if they're negative, they get in. If they're positive, they get sent home, or they get sent for a PCR test. And you just do this at a wide level. And by that time, you've picked up enough of the people who are infectious around to have really suppressed the virus. PCR tests themselves contain this vital information that's just being thrown away. Do not ask me why it's being thrown away. I cannot understand it. I cannot get a straight answer, except I have had it confirmed by the top people in the world in this profession and others that is the case. They collect it for the purpose of some studies, but they don't collect it for individuals. I don't know why. I don't know why. And I think the issue of pre-infectiousness can be handled through more frequent testing would be the way to go there. Anyhow, as I said, this is not rocket science. Please correct me if I'm wrong, that this was nothing other than obvious to all of you. I think the main message here is to find out that our policy makers deciding on testing have got aren't thinking in these terms. And that's really, really the current dilemma we face. At least for most of the world. But if you want to eliminate the virus, I think it's going to matter for that too. That's it. All done. I will now stop the screen share.
Right. Well, anyone, any questions?
I have a question. Hi, Joshua. So it seems like you're focusing a lot on the fact that by using PCR, we're erroneously isolating people in that phase T3 to